Well, hello and welcome to our webinar today. In this month's webinar, we are going to focus on a practical overview of sweep frequency response analysis of power transformers. So, without further ado, let's get started. Sweep frequency response is a major advance in transformer condition analysis, allowing visualization of the inside of a transformer's tank without costly detanking. This is done by performing a simple measurement looking at how well a transformer winding transmits a low voltage signal that varies in frequency. Just how well a transformer does this is related to its impedance, the capacitive and inductive elements that are intimately related to the physical construction of the transformer. Changes in frequency response as measured by SFRA techniques may indicate a physical change that has occurred inside the transformer and thus a change to the transformer's impedance. The cause of the impedance change then needs to be identified and investigated. Now, let's not get ahead of ourselves. First, we need to understand why the transmission of a low voltage signal along a transformer's winding is influenced by frequency and impedance. No circuit is without some resistance, whether desired or not. Resistive and reactive components in an AC circuit oppose current flow. The total opposition to current flow in a circuit depends on its resistance, its reactance, and the phase relationship between them. Impedance is defined as the total opposition to current flow in a circuit. The equation shown is the mathematical representation for a magnitude of impedance in an AC circuit, where impedance, or Z, equals the square root of the sum of the squares of resistance plus net reactance. In an inductive AC circuit, the current is continually changing and it's continuously inducing an EMF. Because this EMF opposes the continuous change in the flowing current, its effect is measured in ohms. This opposition of the inductance to the flow of an alternating current is called inductive reactance. I equals V over inductive reactance is the mathematical representation of the current flowing in a circuit that contains only inductive reactance. The value of X sub L in any circuit is dependent on the inductance of the circuit and on the rate at which the current is changing through the circuit. This rate of change depends on the frequency of the applied voltage. X sub L equals 2 pi FL is the mathematical representation for inductive reactance, where pi is a constant representing approximately 3.14. F is the frequency, and L is the inductance measured in henries. The magnitude of an induced EMF in a circuit depends on how fast the flux that links the circuit is changing. In the case of self-induced EMF, such as in a coil, a counter EMF is induced in the coil due to the change in current and flux in the coil. This counter EMF opposes any change in current, and its value at any time will depend on the rate at which the current and flux are changing at that time. In a purely inductive circuit, the resistance is negligible in comparison to the inductive reactance. The voltage applied to the circuit must always be equal and opposite to the EMF of self-induction. Capacitive reactance is the opposition by a capacitor or a capacitive circuit to the flow of current. The current flowing in a capacitive circuit is directly proportional to the capacitance and to the rate at which the applied voltage is changing. The rate at which the applied voltage is changing is determined by the frequency of the supply. Therefore, if the frequency of the capacitance of a given circuit is increased, the current flow will increase. It can also be said that if the frequency or capacitance is increased, the opposition to current flow decreases. Therefore, capacitive reactance, which is the opposition to current flow, is inversely proportional to frequency and capacitance. Capacitive reactance, or X sub C, is measured in ohms, as is inductive reactance. X sub C equals 1 over 2 pi Fc is a mathematical representation for capacitive reactance. Pi, once again, is a constant representing approximately 3.14. F is the frequency of the supply in hertz, and C is the capacitance measured in farads. The relationship between resistance, reactance, and impedance is shown here. The current through a certain resistance is always in phase with the applied voltage. Resistance is shown on the zero axis. The current through an inductor lags applied voltage by 90 degrees. Inductive reactance is shown along the 90-degree axis. Current through a capacitor leads applied voltage by 90 degrees. Capacitive reactance is shown along the negative 90-degree axis. Net reactance in an AC circuit is the difference between the inductive and capacitive reactance. The equation X equals the inductive reactance minus the capacitive reactance is the mathematical representation for the calculation of net reactance when X sub L is greater than X sub C. The equation X equals X sub C minus X sub L is the mathematical representation for the calculation of net reactance when X sub C is greater than X sub L. Impedance is the vector sum of the resistance and net reactance in a circuit, as shown here. The angle theta is the phase angle and gives the phase relationship between the applied voltage and the current. Impedance in an AC circuit corresponds to the resistance of a DC circuit. The voltage drop across an AC circuit element equals the current times the impedance. The equation V equals I times Z is the mathematical representation of the voltage drop across an AC circuit. Now, let's look at impedance in a resistive inductive circuit. Impedance is the resultant of a phasor addition of resistance and inductive reactance. The symbol for impedance is Z. Impedance is the total opposition to the flow of current and is expressed in ohms. The equation Z equals the square root of the sum of the squares of resistance and inductive reactance is the mathematical representation of the impedance in an RL circuit. All right, let's work through an example. Let's say we have a 100 ohm resistor and 60 ohms of inductive reactance, and they're in series with a 115 volt applied voltage. What is the circuit impedance? Well, to find it, let's work through the mathematics. So, we can have 100 squared plus 60 squared. That would give us 10,000 plus 3,600. Or we would now have 36,000. Taking the square root of that provides us with an impedance of 116.6 ohms. All right, now let's look at impedance of resistive capacitive circuit. In a capacitive circuit, as in an inductive circuit, impedance is the resultant of phasor addition of resistance and capacitive reactance. The equation Z equals the square root of the sum of the squares of resistance and capacitive reactance is the mathematical representation for impedance in an RC circuit. Once again, let's work through an example. So here we will have 50 ohms of capacitive reactance and 60 ohms resistance, and they're going to be in series across a 110 volt source. So, what is the impedance? Well, once again, let's do the mathematics and plug in our variables. 60 squared plus 50 squared would give us 3,600 plus 2,500, or 6,100. Taking the square root, we see that the impedance is equal to 78.1 ohms. Now let's look at impedance in a resistive, capacitive, inductive circuit. Impedance in an RCL series circuit is equal to the phasor sum of resistance, inductive reactance, and capacitive reactance, as we see here. Once again, we can use the equation impedance equals the square root of the sum of the squares. Although net reactance is now represented as either X sub L minus X sub C squared, or it can be represented as X sub C minus X sub L squared. And these would be the mathematical representations of impedance in an RCL circuit. Now, because the difference between X sub L and X sub C is squared, the order in which the quantities are subtracted does not affect the answer. All right, let's work through another example. So here we're going to find the impedance of a series resistive, capacitive, inductive circuit where resistance is equal to 6 ohms, inductive reactance is 20 ohms, and capacitive reactance is 10 ohms. To calculate the total impedance, again, we can work through the mathematics and simply plug in the known variables. So, let's work our way through. And here we see our impedance is equal to 11.66 ohms. Impedance in a parallel RCL circuit equals the voltage divided by the total current. So, total impedance would equal the total voltage divided by the total current. And that would be the mathematical representation of the impedance in a parallel RCL circuit. All right, now let's move on and talk about the theory of SFRA fundamentals. The primary objective of SFRA is to determine how the impedance of a test specimen behaves over a specified range of applied frequencies. The impedance is a distributed network of active and reactive electrical components. The components are passive in nature and can be modeled as resistors, inductors, and capacitors. The reactive properties of a given test specimen are dependent upon and sensitive to changes in frequency. The change in impedance versus frequency can be dramatic in many cases. This behavior becomes apparent when we model the impedance as a function of frequency. The result is a transfer function representation of the RLC network in the frequency domain. Now, a standard definition of frequency response analysis, or FRA, is the ratio of a steady sinusoidal output from a test object subject to a steady sinusoidal input, or more simply put, signal output divided by signal input equals response. Sweeping through the frequency range of interest gives rise to the S in SFRA, to distinguish it from impulse methods where the response is estimated rather than measured. The basic measurement is shown here. To remove the effects of test leads, a 3-lead system is used to measure both the input and output voltage simultaneously. Coax test leads of 50 ohms are used to apply the source voltage and measure the voltage as V sub in. Consequently, V sub out is referenced against the 50 ohm test lead to ground. Frequency response analysis plots the ratio of the transmitted voltage waveform to the applied voltage waveform in decibels. The response in dBs is calculated via the equation response in decibels equals 20 log sub 10 times the voltage out divided by the voltage in. The impedance attenuates the input voltage signal. Individual passive components such as inductors, capacitors, and resistors have identifiable and distinct frequency responses. In practice, however, there is no such thing as an ideal inductor, an ideal capacitor, or an ideal resistor. Each has elements of the other components. Consequently, the responses contain elements of each component, although denominated by their normal type. Now, the expected response for a short circuit at any frequency is that V sub out is equal to V sub in, as impedance, or Z, is equal to 0. This equals 0 dB across the swept frequency range. An ideal resistor reduces the output voltage across the entire swept frequency range. A 50 ohm resistor would give an output voltage half the input voltage. This would be a straight line at approximately 6 dB down, or minus 6 dB, as seen here. A 500 ohm resistor would give a response at approximately 20.8 dB down, or minus 20.8 dB. An open circuit would, in theory, provide infinite impedance and an output voltage of 0. Now, we cannot calculate this as a dB value, but it equates to infinite dB down. An ideal inductor at low frequency looks like a short circuit. As frequency increases, so does the impedance, heading toward an open circuit. The response for an ideal inductor is shown here. It starts at 0 dB and then shows a characteristic roll-off on the log scale as frequency increases. An ideal capacitor looks like an open circuit at low frequencies, but at high frequencies it looks more like a short circuit. The typical response shows a response which climbs towards 0 as frequency rises, as we see here. Now, let's also talk about resonance. Resonance occurs in an AC circuit when inductive reactance and capacitive reactance are equal to one another. X sub L equals X sub C. When this occurs, the total reactance X equals X sub L minus X sub C becomes 0, and the impedance is totally resistive. Because inductive reactance and capacitive reactance are both dependent on frequency, it is possible to bring a circuit to resonance by adjusting the frequency of the applied voltage. Resonance frequency, or F sub res, is the frequency at which resonance occurs, or where the X sub L equals X sub C. The equation F sub res equals 1 divided by 2 pi, the square root of inductance times capacitance, is the mathematical representation for resonant frequency. At low frequencies, the capacitor will dominate and the arrangement will look like an open circuit. Example, impedance approaches infinity. As frequency rises, the impedance of the capacitor will fall, but the impedance of the inductor will rise. At high frequencies, the inductor will dominate and the arrangement will look like an open circuit. Example, the impedance, or Z, approaches infinity. The overall impedance of the arrangement is Z, which can be plotted against frequency as we see here. The point of minimum impedance is the resonant point and is where the impedance is equal to the resistance, R. This occurs when X sub L equals X sub C. Generally, for a series combination at resonant frequency, we have the following. The reactance of the capacitor and inductor are equal. Impedance is minimum for given values of capacitance, inductance, and resistance. The impedance of the circuit is equal to R, or impedance equals resistance. The voltage applied by the source is in phase with the current. The current is maximum for given values of capacitance, inductance, and resistance. The power dissipated in the circuit is maximum for given values of C, L, and R. If we were to measure the circuit using an SFRA test set, we would plot the response in decibel rather than in ohms. Using equation, response in decibels equals 20 log 10 times the voltage out divided by voltage in, and equation voltage out divided by voltage in equals 50 divided by the impedance plus 50. The response D in decibels for an impedance Z is given by the equation D equals 20 log times 50 divided by the impedance plus 50. Plotting D for the series impedance of the figure shown yields the graph that we see here. Clearly, in decibels, a series resonance yields a maximum. This relates to the capacitive climb followed by the inductive roll-off. A maximum in an SFRA plot, therefore, corresponds to a series arrangement of some form that has reached a resonance. Now let's talk about parallel arrangements. At low frequencies, an inductor will dominate, and the inductor will look like a short circuit. Example, the impedance approaches zero. As frequency rises, the impedance of the capacitor will fall, but the impedance of the inductor will rise. At high frequencies, the capacitor will dominate, and the capacitor will look like a short circuit again. Z approaches zero. The overall impedance of the arrangement is Z, which can be plotted against frequency as we see here. The point of maximum impedance is the resonant point. This occurs when X sub L equals X sub C. Generally, for a parallel combination at resonant frequency, we have the following. The reactance of the capacitor and inductor are equal. Impedance is a maximum for given values of C, L, and R. The impedance of the circuit is equal to R, or impedance equals resistance. The voltage applied by the source is in phase with the current. The current is minimum for given values of C, L, and R. The power dissipated in the circuit is minimum for given values of C, L, and R. Now, if we were to measure this circuit using an SFRA test set, we would plot the response in decibels rather than in ohms. We can plot the response D in decibels for an impedance Z as given by the equation D equals 20 log sub 10 times 50 divided by the impedance plus 50. Again, noting that Z is a function of frequency and is complex in nature. Plotting D for the parallel Z yields the graph that we see here. At low and high frequencies, the impedance approaches the value of R, which in this case is 335 ohms. We can calculate the dBs the R alone would yield, and that would come out to approximately minus 17.5 dB as shown in the graph. Clearly, in decibels, a parallel resonance yields a minimum. This relates to the inductive roll-off followed by the capacitive climb. When a minimum occurs in an SFRA plot, this corresponds to some parallel arrangement of an inductor and a capacitor within the transformer. Now, in practice, there is no such thing as an ideal capacitor, an ideal inductor, or an ideal resistor. They each have elements of the other components. To demonstrate, we can look at the response of a small wound coil, a non-ideal inductor. We can see two distinct effects. A low frequency effect where there is a resistance which prevents the coil having 0 dB response at low frequencies. A high frequency effect where turn-to-turn capacitance counteracts the continued roll-off of the inductance. At higher frequencies around 200 kHz, the inductive roll-off is replaced by a capacitive climb. This is where the capacitance between the coils of the specimen counteracts the effects of the inductive element. There is another effect in this coil around 1 MHz. This may relate to its construction in layers, where mutual inductance and capacitance between layers begins to have an effect. The SFRA response for this coil is shown on a log scale. This representation of data tends to highlight low-frequency responses. The same data using a linear scale is shown here. The resonance around 900 kHz are now less dramatic. The linear scale tends to highlight high-frequency responses. The display of data in log and linear formats helps to identify differences between traces. Let's talk now about interpreting results. A SFRA open circuit test will show the response of core and windings, while a SFRA short circuit test only shows the response of windings. Each frequency range corresponds to different components in the transformer. Some general frequency ranges are 20 Hz to 2 kHz. Here we look at the main core deformation, open circuits, shorted turns, residual magnetism. 10 kHz to 20 kHz, now we see bulk winding component and shunt impedance. 20 kHz to about 400 kHz, deformation within the main windings, and 400 kHz to 1 MHz tap windings. However, keep in mind that each transformer will have specific responses, and the frequency range given is for general reference only. All right, let's work through some examples. A high voltage Y winding response. This example shows a typical high voltage Y winding response. All three phases show similar responses at low frequencies with the following characteristics. The center phase has a slightly increased impedance, more negative dBs, at low frequencies. The center phase has 1 resonance and the outer phases 2 resonance below about 1 kilohertz. The outer phases are very similar at low frequencies. The 3 phases come back together as frequencies rise toward 10 kilohertz. The 3 phases show regions of similarity and regions that are not similar across the frequency range. This example shows the response for 3 phases of a high voltage delta winding. This is a characteristic response at low frequencies. The center phase has a slightly higher impedance, more negative response at lower frequencies. The center phase is different to the outer phases at the first resonance below 10 kilohertz. The center phase is more like the outer phases as we rise in frequency. And all 3 phases have the same basic shape above about 100 kilohertz. This example shows the response for 1 phase of a transformer tested at 9 different tap positions. Notice that the linear scale is selected since the SFRA changes occur in the high frequencies. The main winding response below 25 kilohertz remain unchanged. Tap winding responses show stepwise variations. This example shows the SFRA response taken after an incident, shorted turns. 1 phase has clear inductive roll-off associated with short circuit measurements. Variation is a clear indicator of shorted turn on the A phase. This example shows the SFRA response taken of the high voltage delta winding at the factory. This example shows the initial SFRA response taken of the high voltage delta winding in the field. The same phase is compared to the factory response upon arrival at the field site. Low frequency responses show offset due to core magnetization. Results are acceptable, but the test is repeated for confirmation. This example shows the SFRA response taken after demagnetization of the high voltage delta winding in the field. After demagnetization, the low frequency offset is now removed. The high frequency responses remain unchanged. Now, some site noise as low dB response is not unusual. This example shows the SFRA response of 1 phase of a transformer measured with and without oil. The blue trace represents the response without oil. The white trace represents the response with oil. Some site noise as low dB response is not unusual. Removing oil lowers capacitance and resonances tend to shift to higher frequencies. In its standard application, a fingerprint reference curve for each winding is captured when the transformer is new or when it is in known good condition. These curves can later be used as reference during maintenance tests or when there is a reason to suspect a problem. Reference results are preferred but not essential. Results of a sister unit from the same manufacturer may serve in their stead. Several examples of internal winding movement and related failures being detected by SFRA are available where diagnosis was made without use of reference results. The most reliable application of tests is the time-based comparison, where curves are compared over time on measurements from the same transformer. Another method utilizes time-based comparisons between sister transformers with the same design. And lastly, a construction-based comparison can, under certain conditions, be used when comparing measurements between windings within the same transformer. These comparative tests can be performed before and after transportation, after severe through faults, before and after overall, and as diagnostic tests if you suspect potential problems. One SFRA test can detect winding problems that require multiple tests with different kinds of test equipment, or problems that cannot be detected with other techniques at all. The SFRA test presents a quick and cost-effective way to assess if damage has occurred or if the transformer can safely be energized again. If there is a problem, the test result provides variable information that can be used when determining further action. To make an SFRA measurement, a transformer must be prepared as it would be for power factor and capacitive measurements. Each winding section, high voltage and low voltage, are analyzed separately. Transfer function measurements from high voltage to low voltage may also be made, but these are less effective at determining movement. Short-circuit SFRA measurements made, for example, by performing an SFRA on a high-voltage winding with the low-voltage winding shorted, provides further information about winding integrity and relates to transformer leakage reactance. So, open circuit test. An open circuit measurement is made from one end of a winding to another with all other terminals floating. For a delta winding, connections would be H1 to H3, for example. For a Y winding, measurements are taken from high voltage terminals to neutral, such as H1 to H0. Short circuit tests. A short circuit measurement is made with the same SFRA test lead connections as an open circuit measurement, but the difference that another winding is short circuited. To ensure repeatability, it is recommended that the 3 voltage terminals on the shorted windings are all shorted together. This would mean, for example, shorting X1 to X2, X2 to X3, and X3 to X1. This ensures all 3 phases are similarly shorted to give a consistent impedance. Any neutral connections available for the shorted windings should not be included in the shorting process. And interwinding tests. An interwinding measurement is from one winding to another with all other terminals floating. This would include, for example, H1 to X1 on a double wound transformer, or H1 to Y1 on an auto transformer with a tertiary. Note that H1 to X1 on an auto transformer is not an interwinding measurement, but an open circuit measurement on the series winding. Interwinding measurements are usually considered as optional tests, or tests for further investigation when open circuit and short circuit tests are inconclusive. And here we can see some typical test connections. And here are some additional typical test connections. All right, let's go through some frequently asked questions. Is there a published standard for SFRA? Well, The IEEE guide for SFRA is IEEE C57.149, Guide for the Application and Interpretation of Frequency Response Analysis for Oil-Immersed Transformers. Other relevant SFRA documents include IEC 60076-18, Edition 1, 2012, Standard DL/T911-2004, and SIGAR Technical Brochure Number 342, April 2008. Are other electrical tests necessary if I perform an SFRA? Yes. Each test will provide a different piece of data on the transformer. A power factor test looks at the insulation of the transformer. Turns ratio and winding resistance tests reveal the condition of the windings. SFRA provides information about the mechanical integrity of the transformer and can help you identify or determine if a transformer has sustained any mechanical damage. Each electrical test you perform gives a bit more insight, and together they form a more complete picture of the transformer's health. Sometimes a second opinion from one or more tests on the same component can help you confirm a suspected problem. Do I have to perform electrical tests in a particular order? Well, excitation current and SFRA should be completed first and the winding resistance test last. This is to avoid any residual magnetism from the winding resistance test from affecting the results of the other tests. However, if your winding resistance test set can demagnetize the transformer efficiently after the test is complete, you will not have to worry about the test sequence. Will SFRA work on a dry-type transformer? Yes. SFRA looks at the response of the complex RLC network inside of a transformer. You can perform baseline or reference measurements on dry-type transformers and compare results over the years. For dry-type transformers, you need to be aware of the effect that ground capacitance can have on the traces. Additionally, the response on the low side may have slight deviations because of low signal levels. A very good ground plane will produce more repeatable measurements. Can I perform SFRA before oil filling a new transformer? Well, per IEEE C57.149, testing with oil is the most common and preferred method for frequency response analysis. Special consideration should be given to safety when testing a transformer without oil so that excessive voltages are not applied. Presence of oil changes the frequency response. Results obtained with and without oil will cause variations in the SFRA traces. Often the manufacturer fills and drains the transformer before shipment. You should be aware of the consideration in which an SFRA test was performed before shipment from the factory. Does ambient temperature affect SFRA readings? Well, IEEE C57.149 states that large temperature differences, typically much more than 10 degrees Celsius, between two measurements will slightly influence the response at higher frequencies. For all practical purposes, the effective temperature on SFRA measurements is very small and can be ignored unless there is big temperature variations between the two comparison traces. What is the smallest rated transformer that I can use SFRA on? Well, there is no industry guideline for using SFRA based on a transformer's VA rating. In theory, you can perform SFRA on a transformer of any size, and if subsequent tests are performed under similar conditions, the results can be compared and analyzed. Other electrical tests like transformer turns ratio, excitation current, and DC insulation tests will also give valuable information on smaller transformers. And that concludes our webinar for this month. Again, if you like the content that we're producing here at Vector, please remember to hit that subscribe, check that notification bell, and hit that thumbs up. It really does help the YouTube algorithm and really helps to support our channel. So, until next month, I'm Tom Sandry.